So again, today all we're going to be doing is drawing some pictures. Let's begin. Okay, a little bit of preamble here. Whether you write this down or not, it's completely up to you. We've seen already that electrically charged objects are able to exert forces of attraction and repulsion on one another without these objects actually being in contact. And what do we call this again? This being able to apply a force without being in touch? Action at a distance. If you prefer, using the force. Right? That ability to apply a force without any contact. Action at a distance. Okay? This notion of electric field is used by science to describe how charged objects are able to exert forces on one another from a distance. So it's really, if you go way back to that first unit, it's an example of a scientific model. It's a way to describe and explain something that's happening that we can't really see, right? We can't explain this force. And so we come up with this idea of the force field, and it helps us sleep better at night because we can explain it. It's similar to the idea that the Earth's gravitational field is responsible for exerting an attractive force on objects near the Earth. So an electric field is thus defined as, and maybe you want to jot this one down, it is a region of influence around a charged object. Can be made visible when small objects like grass seeds or pepper grains, anything kind of small, little bits of paper, are placed near an electrically charged object. Okay, so in A, this is an individual, a singular positive charge. You've seen this lots of times already. That should come as no surprise. What does the electric field look like? All going out. Exactly. Right? Something like that. What do I look for? Arrowheads going out. If you miss the arrowheads, it's wrong. If you point them in, it's wrong. I'm sorry. Do it right. It's like going through a red light on your driver's test. You fail, try again. Do it right. Okay? How many arrows do I need on there? It doesn't really say how strong it is, right? But what if I were to... Colin, you don't have an earbud in, do you? What if I were to say it's... if I had that and then I asked you to draw a stronger one, what would a stronger one look like? Longer arrows? Shorter arrows? If it was a stronger field, it would have more, because it's the density that matters, right? More arrows. So they'd be closer together.
Would it just tell you that that's...
Yeah, if I said here's a field, if it's doubled in strength, then it would have to have double the number of arrows. I said if they were vectors, it would be like that, Colin. But these are not vectors, these are field lines, and it's the density of the field lines that matter. Does the Earth have a charge? I believe the Earth is more or less electrically neutral. Okay. What if you have a positive charge and a negative charge? Then the arrows go from positive to negative. And so it would sort of look like this. And I would expect arrowheads sort of over there as well as in here. Okay? It doesn't need to be neat and pretty. As you can tell, I'm not that neat or pretty. Thanks, mate. These are gimme questions on the test. Don't blow this. Don't mess up. Away from positive towards negative. It's pretty simple. What about two positives? Away, away. You've got a region where there is no electric field, right? Or it's actually very weak, right? Why is it weak in here? No, because the density is not very, right? It's not dense. There's hardly any lines in there. How much should I give you for that? A single mark, you guys. It's not hard. What, you want one mark for every arrow? Well, sorry, not going to happen. No, one mark. It's easy. Ooh, they curve. Positive, now this is a negative plate, so it's flat, right? It's got charges distributed throughout it, so away, away, away. And then in here, they're going to start to...
Is that a positive circle one?
Yep. Right? And then is there field lines over here? Sure is, towards, right? Yeah, so? Pardon me? They're all going towards negative and away from positive. Good? What about a positive and a negative set of plates like this? Colin, put the phone down, please. You were doing that the other day. Oddly enough, we got positive on the right, we got negative on the left. So we're going to go away from positive. And these lines should be relatively the same distance apart, equidistant, because the electric field is uniform throughout. The density, the distance between them is the same. Okay? So those are all like that. And then over here, same idea. Towards, towards, towards. Now, oh, wait a second. Where do you think it's stronger here? I'm going to label areas A, B, and C. Where do you think the field is strongest? Why B?
Because there's direct pushing.
Exactly. There's field lines from the negative, and there's field lines from the positive. In fact, I should probably, and you might get a little mad at me here, but that's okay. It should probably be better described like this, right? Oh, hang on. Right? The blue ones is the negative, right? You'll notice that there are 6 of them here. I counted them. And there's 6 blues here, 6 blacks there. But in the middle, there's actually 6 blues and 6 blacks, right? So in fact, it really should be twice the strength inside. You can redraw it on the, just however you want to deal with it, right? But I want you to understand that, right? So that it is stronger inside than it is outside. Is this easy stuff? Yeah, it's pretty easy. That might even be the last slide. It is the last slide.